Today's discussion is on intermolecular forces. And as we can see right here, intermolecular forces, many times we abbreviate them by just writing IMFs. And on the AP test, you are certainly more than welcome. Once you write intermolecular forces once, if you want to call them IMFs after that, that is perfectly fine. But intermolecular forces, remember, inter versus intra, are the forces of attraction that exist between one molecule and another. So far in this unit, we've been talking about bonding, and we've been talking about those intramolecular attractions. So remember that in water, for example, you've got HOH, and that right there is the intramolecular attraction. Again, intra just refers to, that's the actual covalent bond. Okay, when we talk about intermolecular attractions or intermolecular forces, we're talking about, here's another water molecule, and there, right here, there is a force of attraction between one water molecule and another. And anytime I talk about intermolecular forces, that's the word that I use, is I always use the word between. So that is the intermolecular forces, and that's between one molecule and another. Okay, now intermolecular forces, why do we use them? We're going to use them for a lot of things, unfortunately, in chemistry. This is a pretty big topic. They are used to describe why one atom or a molecule or something like that has a greater boiling or freezing point than another, why one gas might behave more or less like an ideal gas. There's lots of different ways that we use intermolecular forces. That's just a couple of examples. But let's go through intermolecular forces, and then we'll talk a little bit more about where you might see them, the types of questions that you might see, etc. So there are three main types of intermolecular forces. The first one are called London dispersion forces. Again, you can abbreviate that by just writing LDFs. So London dispersion forces, again, is the attraction between one atom or one molecule and another molecule. Okay, it is the weakest, typically. Let me underline that. Typically or usually, it is the weakest of the three intermolecular forces. If everything else is the same, then London dispersion is the weakest. Okay, and we're going to see some examples when it isn't. But in most cases, it is the weakest of the three intermolecular forces. Now, when do London dispersion forces occur? They occur between two non-polar molecules. That's why we've waited so far in this year before we started talking about intermolecular forces, is because you really have to be able to distinguish between a polar molecule and a non-polar molecule. And because if a molecule is non-polar, then it only has London dispersion forces of attraction between them, which again are very weak. Now what happens is, like, let's say in an atom of, let's say, neon. Okay, a neon nucleus has 10 protons. So there's our nucleus right there. And then you've got these 10 electrons. 1s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and let's say the way that I drew this, just happened to draw it this way, is that right now there's more negative charges on the right-hand side than there are on the left-hand side. Again, just because that's how I drew it. And so what that does is it creates what we call this instantaneous dipole moment. So even with nonpolar compounds, if just by chance more of the electrons happen to be on one side of the atom than on the other at any given time, then you've created this instantaneous dipole, where now you've got a partial negative charge over here, and you've still got that positive charge there. So it's kind of like for a moment, it turns into this polar molecule where you've got a negative side and a positive side, just like a polar molecule does. And when that happens, that's where you can have some London dispersion forces. So for example, neon, in this case, you could have another neon atom over here that has, again, the 10 protons and has more electrons over on the right-hand side again, because remember, electrons repel each other. Okay, and then this attraction between the positive part of one neon atom and the negative part of another part of a neon atom is that attraction right there is a London dispersion force. Okay, now notice I'm using neon. Neon is an atom, and that's why I said here it can exist between why one atom or a molecule has a greater boiling. So it can happen just with atoms as well. So the attraction between one nonpolar atom and another, or the attraction between one nonpolar molecule and another, is where we see London dispersion forces. Okay, so again, kind of what we just talked about here, they don't have a permanent dipole. It's just that instantaneous dipole. As one molecule approaches another, the electrons are displaced, like we just talked about. This causes these small temporary dipoles to be set up. And again, what we call those, because it's, again, a temporary one, is we call them an induced dipole. So it's kind of like you're forcing, when someone is pregnant and they induce them, they're forcing them, trying to force their body into having the baby. We're kind of forcing this atom up here. Oh, if we move these atoms close enough together, the electrons repel each other enough that these electrons here push those other electrons to the other side, and now we've got this attraction here between the nucleus of one neon atom and the electrons of another. Now, these attractions, again, are called London dispersion forces. Now, they do exist between all atoms and molecules. Now, what that means is it means that if the molecule is nonpolar, then it only experiences London dispersion forces. If the molecule is polar, it experiences London dispersion forces and possibly some other types of intermolecular forces as well. So nonpolar molecules only experience London dispersion forces, where all the other molecules have other intermolecular forces as well, but they also have London dispersion forces. So if on the AP test they ask you, for example, water, for example, what are the intermolecular forces that exist between water molecules? One of them that you're going to list is London dispersion forces. Because again, London dispersion forces exist between all atoms and molecules, whether they're polar or nonpolar. Okay? But again, nonpolar ones only have London dispersion forces. That's it. Now, let's talk about what happens as you move around in terms of the periodic table. So the noble gases, and they're down here. We'll talk about those in just a second. But the two things that affect London dispersion forces are, number one, the surface area, and number two, what's called the polarizability. Okay, and again, we're going to talk about what both of those mean here in just a second. So polarizability, in turn, increases with the increased number of electrons. So let's look at, for example, helium versus, let's go down the noble gases, and xenon. Okay, let's think about again, here they're talking about the electron cloud. Helium has 2 electrons. Okay, whereas xenon, and I'm not going to go anywhere near, xenon has 54 electrons. Now, when we talk about polarizability, we're talking about the bigger the electron cloud, which is in this case is xenon, the bigger the electron cloud, the more polarizable that atom or molecule becomes. Because the likelihood of one or more of those electrons being on one side of the atom than the other is greater. So the more electrons that atom has, the more polarizable the atom is, and therefore the greater London dispersion forces that atom or molecule is going to have. So polarizability is the more electrons there are, the more likely they are to be on one side of the atom or the other, which again creates that small temporary induced dipole, and therefore has greater London dispersion forces. So the greater the polarizability, the larger the electron cloud. The larger the electron cloud, the greater the London dispersion forces are. Okay? So, in short, molecules that have larger surface areas have more electrons, which have greater polarizability. Okay? And we're going to talk about surface area a little bit more here in just a minute. Okay? So, polarizability is a big, big word. when you're dealing with London dispersion forces. That the more electrons there are, the more polarizable the atom or molecule is, and therefore the more that the London dispersion forces affect the strength of attraction between those two atoms or molecules. So let's look here at the noble gases. Look at a couple of examples. Okay, so boiling points of the noble gases, descending group 8A, the atoms of the elements get bigger. Okay, so we can look at the periodic table and go, well, duh, as you go down the periodic table, the number of protons, the number of neutrons, electrons increase, so the molar mass gets bigger. Okay, they have more electrons, they have more surface area, and this increases the London dispersion forces between them. Okay, and if the London dispersion forces are stronger, that means they're more attracted to each other. Well, the more attracted they are to each other, the harder they are to break apart to turn into gases, or to turn, gases into liquids, or solids into liquids, or liquids into gases. So we'll notice here that as you go down the periodic table, what happens to the boiling points? You'll notice that of the 5 of them there, helium has the greatest boiling point. Okay? Neon, negative 246. Argon, negative 156. Xenon, negative 108. Okay? So the boiling point, so the point at which it goes from a liquid into a gas for helium is the lowest, which means it's held together the weakest. Whereas notice remember, these boiling points are actually going up. Okay, as you go down this list, it's becoming less and less negative. So the boiling points are going up. Okay, now why does the boiling point go up? Because again, as these atoms become more and more polarizable, the size of the electron cloud is increasing, and as the size of the electron cloud is increasing, again, it's more likely to create those induced dipoles, which again therefore creates a stronger London dispersion force. Now here's a quick note. Here's a couple of them actually. Okay, molar mass is oftentimes incorrectly used to describe London dispersion forces. For example, they might ask you on the test, why does xenon have a greater boiling point than helium? And people say, well, xenon's more polarizable because it has a greater molar mass than helium does. Okay, which is not correct. So one might say that krypton has a greater boiling point than neon because krypton has a greater molar mass. So although that is correct, you can start by thinking that way. So when we're talking about neon versus krypton, I look at the periodic table and I go, okay, krypton has a molar mass of 84, neon has a molar mass of just over 20, krypton has a greater molar mass. And so therefore, and I'm not going to say that at all on the test, is I can look at the periodic table and go, okay, molar mass is greater, therefore it has a larger electron cloud, and that's the key, because krypton has a larger electron cloud than neon, which makes krypton more polarizable, and therefore has greater London dispersion forces, which results in a higher boiling point. That last sentence right there, that's the key. That's how you're going to explain it on the test. If you're comparing two nonpolar molecules to each other, the one that's going to have the greater boiling point or the greater melting point is the one that has the greater London dispersion forces. And we know that based on the size of the electron cloud, which therefore determines how polarizable the molecule is. Okay, now let's talk a little bit more about surface area. Okay, when electron clouds are similar in size, well, how do you know if they're similar in size? Because they have similar molar masses. So something like CH3OH has a molar mass of 12, 28, 32. And let's say we had C2H6, which has a molar mass of 30. Oh, their molar masses are similar, so therefore their London dispersion, they're going to be very similar in their polarizability, which means that they're going to have very similar London dispersion forces. So when electron clouds are similar in size, the difference in the London dispersion forces comes from the difference in the surface area. Okay, a molecule that's more spread out, okay, something like, let's say, like carbon, 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 with, again, I'm not going to draw them all, with a whole bunch of hydrogens on that. That's very symmetrical. That's 5 carbons in a row. That has a very large surface area. Let's say we take that same molecule, though, and we do something like this, where all 5 carbons are kind of in like a 1, 2, 3, 4, 5, kind of a pentagon type shape or something like that. Well, that's much more put together. This has a very small surface area. This has a very large surface area. Okay. So a molecule that's more spread out will have a larger surface area than a molecule that's all clumped up together, or even something like this. What if you had a carbon, 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 like that? There's a 5 carbon molecule that is very symmetrical versus this one where it's all spread out. We know that when that happens, that when the larger the surface area, the more polarizable that molecule is, the more likely it is that the electrons are going to be on one side or the other, so it's going to have a higher boiling point. Okay, so comparing the LDFs of the following 2 molecules, we got H3C, so actually it's kind of like this one I just drew on the right-hand side. So we've got a carbon with 3 hydrogens, then we've got a carbon in the middle, then we've got 2 more carbons that have 3 hydrogens on it. So it's this molecule right here versus the one, well, I should have just left that there, versus C5H12. Okay, the first molecule, this one has a boiling point of 10 degrees. This one has a boiling point of 36 degrees. And again, how would you explain it on the AP test? You would say, since C5H12 has a greater surface area than this molecule here, the London dispersion forces are greater, it's a more polarizable molecule, and therefore it's going to have a greater boiling point. Okay, so that's it for non-polar molecules. Okay, the next type of intermolecular force is what are called dipole-dipole forces. Now again, we have to know the difference between a non-polar molecule and a polar molecule in order for this to work. Dipole-dipole forces exist between 2 polar molecules. So if you don't know if the molecule is polar or nonpolar, you don't know whether it has dipole-dipole forces or not. Okay? If a molecule is nonpolar, it can't form dipole-dipole forces. Okay? There are no, and remember, a dipole, if something has a dipole moment, it means it's polar. So really, it's that attraction between one polar molecule and another. It can be 2 of the same, but again, both of them have to be polar. Okay, so again, let's think about so if something is nonpolar, the only type of intermolecular forces that exist are London dispersion forces. If a molecule is polar, there are dipole forces and also London dispersion forces between them. And again, dipole-dipole forces are typically stronger than London dispersion forces. Again, they may not, and again, we'll see an example of that here shortly. Okay, when molecules have permanent dipoles, so again, that means a polar molecule, and they come close to each other, they're going to arrange themselves so that the negative end and the positive ends of the molecules attract each other. Okay, the complete picture is a little bit more complicated, 3-dimensional, all that stuff, but really we can kind of see if this is a polar molecule here, the negative end is going to be attracted to the positive end of other polar molecules. And the positive end is going to be attracted to the negative ends of other polar molecules. Okay, and so all polar molecules exhibit these intermolecular dipole-dipole forces and also intermolecular London dispersion forces. Okay, and in general, the dipole-dipole forces are greater than London dispersion forces only. Okay, the last type, so let me come back up here for just a second. With dipole-dipole forces, the more polar the molecule, the greater the dipole-dipole forces are. So if one molecule is more polar than another, then the dipole-dipole forces are greater between those molecules and another. The stronger the difference in those electronegativities are, the stronger that attraction is to other molecules. So if you're looking at 2 polar molecules, which one's going to have a greater, for example, NH3 is polar, trigonal pyramidal shape. versus H2S, which is also, this is a bent molecule, but notice they're both tetrahedrals. Oops. They're both tetrahedrals. So therefore, well, which one's more polar? Well, the more electron pairs that are on that central atom, the more polar it is. So between these two, which one would you predict to have a higher boiling point? H2S. And how would you justify that? H2S is a more polar molecule than NH3, so the dipole-dipole forces that exist between its molecules are stronger. The H2S's hold on to other H2S's with more strength than, say, NH3 does. Okay, the last one, so we've got nonpolar London dispersion forces. We've got polar molecules that have dipole-dipole and London dispersion forces. And the last and strongest type of intermolecular force is what's referred to as hydrogen bonding. Okay, hydrogen bonding occurs when the hydrogen of one atom that's bonded to either an N, an O, or an F is attracted to, that's bonded to a small, highly electronegative atom. So it has to be one of those three. Those are the only three. There can't be more. Okay? Is attracted to a small, highly electronegative element in another molecule. So the hydrogen must be bonded to an N, an O, or an F, and then it must be attracted to an N, an O, or an F on another molecule. Okay, so in other words, a hydrogen atom that is covalently bonded to an N, an O, or an F, so again, there's our covalent bond, that's the intramolecular bond, is attracted to via a hydrogen bond, which again, I don't really like the name because it's not a bond. It's just an intermolecular attraction, but we call it hydrogen bonding. That hydrogen is attracted to an N, an O, or an F on another molecule. Ways that they trick you is they bond this hydrogen to something else other than N, an O, or an F. So we know that the hydrogen bond exists between an H and an N, an O, or an F, but the hydrogen itself must also be bonded to an N, an O, or an F. Now, what happens here is that hydrogen is an exceptional element in that when it forms a covalent bond, its electron is held to one side of the nucleus, leaving the other side completely exposed. So right here on this hydrogen, it only has one electron, and that electron is right here. And again, because these are very electronegative elements, they're able to pull those that electron and this electron closer to itself, which means this other side over here is completely exposed. So any approaching negatively charged group that can get very close to the hydrogen nucleus produces an unexpectedly large electrostatic attraction. So this is kind of the negative side of the hydrogen. This is kind of the positive side of the hydrogen. And when it's bonded to a more electronegative element, again, that allows a significant intermolecular interaction between them. Okay? So really, hydrogen bonding really is a dipole-dipole force, but it's a special type of dipole-dipole force that really, we separate them completely. Okay? So if a hydrogen is bonded to an N, an O, or an F, it does have hydrogen bonding. Okay? So coming back up here, this example that I used right here. Okay? If this hydrogen here is attracted to the N, which it is, so notice the hydrogen is bonded to the nitrogen, and then it's going to be attracted to the nitrogen on another NH3. That again right there is the hydrogen bond. So now that we know that, now coming back to comparing NH3 to H2S, I know that hydrogen bonding is stronger than dipole-dipole forces. So right away, I would say that NH3 is, I would predict to have a higher boiling point than H2S, simply because NH3 experiences all three types of intermolecular forces. It experiences intermolecular hydrogen bonding, dipole-dipole, and London dispersion forces. Whereas this molecule here, H2S, only experiences dipole-dipole forces and London dispersion forces. Okay, that hydrogen is not bonded to an N, an O, or an F, so it can't form a hydrogen bond with another H2S molecule. Okay, So there's two things that happen because of hydrogen bonding. Again, they have unusually high boiling points, which means that's because they are the strongest type of intermolecular force. Okay, and substances that have hydrogen bonding tend to be more viscous, which means that they flow. If you pour them, like syrup has a very high viscosity, so they flow slower because they're more attracted to each other, and so it's harder for them to move away from each other. And basically, as you pour things, to separate from each other so they can move. Okay, and again, both of these ideas are explained by the increased attraction between molecules caused by hydrogen bonding. All right, so here's an example problem of a type of intermolecular force question you might see. So there's lots of information here. Basically, the question is, which of these four choices correctly shows hydrogen bonding? So let's just go through each of them. So here we notice the hydrogen is a hydrogen bond with a nitrogen, and here a hydrogen bond with an oxygen, or so we think. Remember, it's not just the hydrogen bond that we're worried about. The hydrogen itself in its bonding must be bonded to a nitrogen, an oxygen, or a fluorine. So notice that the covalent bond is between hydrogen and carbon. Okay, so even though the hydrogen is attracted to an N, an O, or an F in another molecule, that still can't be hydrogen bonding because the hydrogen itself is not bonded to an N, an O, or an F. So A cannot be correct. So here we've got an O, hydrogen bonded to an N immediately right away, no. So that one looks right, but then again, you've got a hydrogen bonded to a carbon, so also no. Here's a hydrogen attracted to another hydrogen. Remember, a hydrogen bond is when a hydrogen is attracted to an N, an O, or an F on another molecule when it's bonded to an N, an O, or an F in its own molecule. So here, that's a good start, but then you've got this, you've got all sorts of problems on this one. Okay, but notice, so here's the correct answer. You've got a hydrogen that's bonded to a nitrogen, and then the other hydrogen also bonded to a nitrogen. Do they have to be the same element? Of course not. Could this right here be an oxygen? Yes, it could. Okay, and then the hydrogen in the hydrogen bond is attracted to a nitrogen on another molecule and attracted to an oxygen on another molecule. So that right there is a great example of hydrogen bonding. Okay? Now, on the AP exam, many times they talk about the attraction between one thing and something else, okay? And we need to be familiar with what those terms are. And then we're going to do a little summary here. We're going to look at this little cute thing. And then there's actually that part there as well. So we've got a little bit to go still. So another type of attraction that pops up on the AP exam is the attraction between particles. For example, you put Ca2 plus in water. How attracted is Ca2 plus to the water molecule? Well, Ca2 plus, again, or Na plus, or it doesn't really matter, Al3 plus, those are going to be attracted to the water via what we call, and notice how they call them, this is an ion. Ca2 plus is an ion, and water is a polar molecule, and so we call them ion, because of the ion, dipole forces. Okay, and that's a force of attraction between a charged particle, an ion, and a polar molecule such as water. For example, when you put table salt into water, the salt breaks apart into sodium ions and chloride ions. We're going to get to that in a little bit. Okay, this occurs because NaCl is what we call soluble. That means that when you put salt into water, it breaks into ions. Okay, we're going to get into that in a little bit more detail later on. Okay, so the ion dipole forces that are formed between the polar water molecules, that's the dipole part, and the chloride and sodium ions are what we call that ion dipole force. Now, using Coulomb's law, we can determine that the larger the charge or the smaller the ion, the greater the ion dipole attraction. For example, of these three here, which one is going to be most attracted to a water molecule? Well, remember Coulomb's law, the force of attraction is proportional to the charges over the distance. So if we look at calcium and sodium and aluminum, calcium's a little bit bigger, but it does have a +2 charge. Sodium and aluminum are smaller. Aluminum is the smallest of the three, which means this number on aluminum is the smallest, and aluminum has the greatest charge. So of those three, which one would have the greatest attraction to water? Or another way we could say it, which one would create the strongest ion dipole forces? It would be aluminum. Okay. Now that happens when you put a positively charged or a negatively charged ion into water, in that how attracted is it to the water molecule depends on the charge. It really depends on Coulomb's law, the charge, and on the distance, how big the atom is. Like if you're comparing Na plus versus Cs plus, which one's going to be more attracted to a water molecule? Well, the charges are the same, so then it comes down to distance. So since sodium is smaller and cesium is bigger, the smaller this number is, the bigger this number is. So a sodium ion would be more attracted to a water molecule than a cesium atom would. Okay, now what does that look like? When you draw that, what does that look like? So if you have a sodium ion, you've got Na plus, and you got a chloride ion as well, Cl minus. Okay, when that gets attracted to water, think about water. Water is very, very polar. Water's got like this, and we know that oxygen is significantly more electronegative than hydrogen is. So if we draw those dipoles, they would go this way towards the oxygen. And we have that partial negative charge right here, and the hydrogens have the partial positive charges. And so what happens when you put salt in water is you've got the sodium ion here. Well, think about that. What part of the water molecule is going to be more attracted to the sodium? The hydrogen or the oxygen? Clearly the oxygen. And so many times they'll ask you to draw it, or you'll draw it something like that, where see that right there is the water molecule. Well, they'll say represent water molecules that look like this. And so what you do is you put the oxygen towards the sodium and put the hydrogens on the outside. So we could draw it just like that right there. Now, if it's chlorine though, chlorine has that negative charge. So again, looking at the water molecule, we know that the hydrogens would be the ones, sorry, that hydrogen was too big there. The hydrogens would be the ones that are attracted to the chloride ion because they have the partial positive charge that's going to be attracted to the chlorine's negative charge. Okay, very possible they could ask you a question like that or give you a drawing and make you answer questions about that. So the positive ion has the oxygen closer to it. The negative ion has the hydrogens closer to it. Okay, another type of attraction you can have between molecules is when you have a polar compound and a nonpolar compound. And again, just think about that. Dipole, induced dipole. If something has a dipole, it's polar. If something is nonpolar, it has an induced dipole. So this occurs when a polar molecule and a nonpolar molecule interact. Okay, this occurs primarily when a nonpolar solute is added to water. So if something's nonpolar, you put it into water, you get these very weak dipole-induced dipole forces. And again, London dispersion forces that exist between those that nonpolar compound. Because the dipole-induced dipole forces are much weaker than the dipole-dipole or hydrogen bonding, again, you have they're much less soluble. So NaCl is very soluble in water because it creates these very strong ion dipole forces. Whereas when you put something nonpolar, sometimes the strength of attraction is so weak that they won't even mix, like oil and water. Oil is very, very nonpolar. Water's really, really polar. So they won't even mix at all because there's not enough energy in order to create these dipole-induced dipoles to keep them together. Okay? And a lot of times in chemistry, we use this term like dissolves like. Okay? In terms of if something's going to dissolve in something else, okay, usually when we say like dissolves like, the like is referring to polarity. Okay? Substances with similar Intermolecular forces, in terms of they're both polar, they're both nonpolar, etc., tend to dissolve in each other better. For example, C4H10, which is very nonpolar, it's just 4 carbons in a row, is really soluble in C8H18. Again, also another long nonpolar compound. Okay, it's more soluble in that than it would be in water because, again, nonpolar, whereas water is very polar. Okay? All right, so a quick summary here of intermolecular forces. There's lots of different ways they can ask you questions about these. Okay, most of the time it deals with melting, boiling, freezing points, things like that, but not always. Okay, but anytime they ask you about a phase change, it's going to involve intermolecular forces. Again, molecular, though, remember, deals with covalent compounds. At no point today, when we've talked about London dispersion, dipole-dipole, or hydrogen bonding, did we ever refer to an ionic compound. Okay, these are only covalent compounds. Okay, so when asked about the phase change, the melting, boiling, freezing point, why does this have a greater boiling point? Why does this have a greater freezing point, etc.? You're always going to refer to the intermolecular forces. The weaker the intermolecular forces, the lower the temperature at the phase change. Okay, what about the vapor pressure? Which of these substances would you expect to have the greatest vapor pressure or the weakest vapor pressure? Vapor pressure is the gas above a liquid. So which one's going to have the greatest vapor pressure is the one with the weakest intermolecular forces because it turns into a gas easier. The one with the lowest vapor pressure is the one with the strongest intermolecular forces. Okay, or they can say, here's a bunch of gases. Which one's going to condense first? As you start to lower the temperature, which one's going to condense first? Well, as they hit each other, if the intermolecular forces are strong, they're going to stay together. Okay, so the weaker the intermolecular forces, the easier the substance can break off and form a vapor. Okay, and so therefore the higher the vapor pressure. So weaker IMFs, higher vapor pressure, or let's go back to condensing here. The stronger the intermolecular forces, the easier the gas will return to the liquid state and turn back into a liquid. So you've got 4 gases at the same temperature, same pressure, blah, 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 and they start to lower the temperature. And they say, which one's going to turn back into a liquid first? Which one's going to condense first? Well, the one that when they hit each other, they're more likely to stick together, and that's the one with the stronger intermolecular forces. Okay, viscosity, how quickly something flows, deals with intermolecular forces. Okay, or, and I know I brought this up when we talked about gases earlier, which gas behaves most or least like an ideal gas? Okay, and think about it. Remember, there's 2 things that we consider. Gases don't take up any space, and they're not attracted to each other, even though they are, and even though they do take up space. Well, which one's going to behave least like an ideal gas is the ones that when they hit each other, they're more likely to stick together. Because remember, we pretend like they don't. In an ideal gas, they don't. So a gas that does not behave like an ideal gas is the one that when it hits each other, it sticks together. So the stronger the intermolecular forces, the less a gas is going to act like an ideal gas. Because again, the particles are more attracted to each other because they have stronger intermolecular forces. Okay? When they ask you about intermolecular forces on the AP exam, you always discuss the intermolecular forces of both molecules. Okay, if they ask you to compare SO3 and CO2, you have to talk about, well, CO2 is a nonpolar molecule, therefore it only exhibits London dispersion forces. SO3 is also a nonpolar molecule, also only exhibiting London dispersion forces. However, SO3 has a larger electron cloud and is more polarizable, therefore the boiling point of SO3 would be greater. Okay? And again, only for covalent compounds. If you compare that to NaCl, you don't talk about intermolecular forces ever if it's an ionic compound. Only when you're dealing with all nonmetals, that's when you deal with intermolecular forces. Okay, well, let's look at this here real quick. So some of the ones we talked about, again, the three main intermolecular forces are London dispersion forces. Again, typically energy-wise, pretty weak. Okay, you can also have dipole-dipole forces, which again typically are stronger than you can see here than a London dispersion force. But notice sometimes London dispersions can be kind of high, and if the dipole-dipole is a little bit lower, could you have a molecule that has really big electron cloud and one that's not very polar at all? Could the boiling point of this one be higher? It absolutely could. And what would your reasoning be? The size of the electron cloud in London dispersion outweighs the polarity of the dipole-dipole. Okay? And then you do obviously have hydrogen bonding as well. And again, those are our three main ones. And then again, you can have ion dipole, then the ion-induced dipole, which again, that would be an ion in a non-polar compound. And then you've got dipole, polar, in a non-polar compound. Again, that's like water and oil, where if it's too weak, it won't attract each other at all. All right, last thing here. Sorry, this is taking so long here. Okay. What about an ionic compound? And I bring this in right now because it does relate to boiling points, freezing points, etc., like intermolecular forces do. Okay, we know that when we determine the strength of attraction between covalent compounds, we consider the intermolecular forces. Okay, but what about the boiling point between, say, sodium fluoride, an ionic compound, and magnesium oxide, also an ionic compound? Okay, first of all, ionic compounds always have higher melting points, boiling points, etc. Okay, so right away, because it's ionic, because of those lattice structures that ionic compounds form, those boiling points and melting points are always higher than covalent compounds. So can we use intermolecular forces? Well, again, they're not molecules. Okay, they're not molecules. These are ions. Intermolecular forces only refer to molecules, which again are nonmetals, not ionic compounds. So to determine the strength of attraction between ions, we use what's called lattice energy. And remember, sometimes I call it lattice enthalpy. Same thing. Remember that ionic compounds, it's not just Na plus and an F minus. Remember, not zero, minus. Remember, it's a whole bunch Na plus, Na plus, Na plus, F minus, F minus. There's that lattice structure where there's a whole bunch of them together. Okay, and so we call this lattice energy, and again, it's nothing more than an application of Coulomb's law. Okay, Coulomb's law again tells us that the force of attraction between oppositely charged particles is determined by their charges, and then the inverse square of the distance between the nuclei. So when comparing the boiling point, melting point, etc. of ionic compounds, your discussion must be about lattice energy or lattice enthalpy. Okay, so here we have an example. The boiling point of MgO is 3600. Remember, here it is up here, MgO. The boiling point of NaF is only 1695. Okay, explain why. Why is magnesium oxide so much higher than sodium fluoride? Okay, Coulomb's law. Okay, because in terms of size, sodium and magnesium are right next to each other on the periodic table. They're pretty similar in size. Oxygen and fluorine, right next to each other on the periodic table, very similar in size. So that part doesn't have an impact. However, you've got that Q1, Q2, those are the charges. Magnesium has a +2 charge, oxygen has a -2 charge, whereas NaF only has a +1, -1. The greater the charges, the greater the force of attraction, the greater the boiling point. Okay, if the charges are the same, on here we explain it, the greater the lattice energy, MgO has the greater lattice energy because the charges on the ions are +2, -2, whereas in NaF they're only +1, -1. The greater charges in MgO create a greater Coulombic attraction between the ions, resulting in a higher boiling point. That's a great way to describe it right there, a Coulombic attraction. Okay, now what if the charges are the same though? In this case, and let's come down to the very bottom, if there is a discrepancy between sizes and charges, well, this one's smaller, but this one has a greater charge. Which one is it? Charges, in this case, always have the bigger impact. Okay, LAN, which is +3 -3, is going to have a way bigger boiling point than anything that MGS, which is +2 -2, or KCL, which is +1 -1. That one's always going to win. Charges are always more important with lattice energy. Okay, if the charges are the same though, like here, +1 -1, +1 -1, now we can start looking at the distance, okay, that radius there on the bottom. So NAF does have the greater lattice energy since the charges are equal in both compounds, and the distance between sodium fluorine ions is much smaller. Sodium's smaller than cesium, and fluorine is much smaller than iodine. So the distance between their ions, between their nuclei, is much smaller than the distance between cesium and iodine. And again, that results in a stronger Coulombic attraction between sodium and fluorine, which results in a higher boiling point. Okay, so that's it. So we talked about, this is a long video with a lot of information. We talked a lot about intermolecular forces that only affect covalent compounds. We talked about lattice energy that only affects ionic compounds. There's a lot. This is a really, really important part of the AP exam. And there's, again, just start looking at your homework problems and look at all the different ways they can ask you questions about this, because it is a pretty important part of the AP curriculum.